Go.
Lectrostatics. We're going to be going over Coulomb's law, superposition, what an E field is, potential energy, and Gauss's law.
It's not potential.
Electric potential.
Okay.
Psych? We're going to redo that.
Go.
Okay, so first, Coulomb's law. Coulomb's law, we use this to find the force of which electric charges exert on each other. And the formula for this is F equals KQQ over R squared, where Q1 and Q2 are the charges of the charges. And R squared is the distance between the charges, and K is a constant. The K constant can also be expressed as 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. And you can get these values on the chart that we get, so I'm not going to write them down. Okay, so how to use Coulomb's law. This is a very basic problem. So if you have one charge and another charge that's R distance apart, all you have to do is plug all of these values into F equals KQ over R squared to get final answer of 8.2 times 10 to the negative 8.
Set. Go.
Hi, welcome to the wonderful world of superposition. So essentially, when you're dealing with more than two charges and you want to calculate the force on each one, or the total force or anything, you can treat each one separately. So when there are three charges, you pretend, you just treat this one and you use Coulomb's law to calculate the force, or then you look at this force and this force. So you pretend like the electric fields don't really matter, and you can just use vector addition to add up all your answers. So whatever values each of these are, x, y, and z, in the end you add them vectorially, and you're good. That's the principle of superposition. So essentially you can treat each charge as if the other charges aren't there. Go.
Okay, so we're going to use integrals to calculate the electric field, and we have this ring of charge that's coming, where half of it is coming out of the page. And there's a point charge here that's a distance r away. So we want to find the electric field from a point dq. So what we're going to do is we're going to split up this ring into small dLs, which are infinitesimally small lengths of the charge. And we know that the formula for the electric field is 1 over 4 pi epsilon naught, which is also k, multiplied by dq, which is a small which is a really small charge on the ring, all over r squared. And then what we're going to do, because based on the, let's say this point here in the ring and this point here in the ring, the y components are going to cancel, so we're only left with the x components, and that's why we're going to use cosine theta. So we're going to take the integral of dEx, or dE cosine theta, and we're going to we're going to have to separate the dq into lambda times L, because that is the, lambda is the unit charge per length. So we get the integral of 1 over 4 pi epsilon naught times lambda dl over the square root of x squared plus r squared, which is also r, and multiplied by the cosine of theta, which is going to be x over the square root of x squared plus a squared. Then, once we simplify the integral out, we end up getting qx, which q is the charge on the entire ring, over 4 pi epsilon naught times x squared plus a squared to the 3/2. Yeah, that's it.
Okay, this one is electric potential. So electric potential is defined as the force per unit charge, and it has a unit of volts. And it has three different equations. V equals negative integral of E dot dl, V equals the integrals of dV, V dot Q equals kinetic energy, and V equals KQ over R. You use these three different equations for finding electric potential energy by the different problems. Let's say if you want to use V v equals negative integral of d dot dl. You use this when you want to put the path integrals. Remember where you have a, a sphere here, and then you want to see the different integrals from point 0 to infinity. You want to use the v equals negative e dot dl. And when you want to use this when you have a specific kind of function for v. Q. Well, you can find the kinetic energy by multiplying the voltage and the Q, and Q is the charge on the sphere. And this is another way you can find the voltage by saying that V equals KQ over R, and this equals to 1 over 4 pi epsilon naught times Q over R.
You merely adopted Gauss's law. I was born by it, molded by it, raised by it. What is Gauss's law? Gauss's law is an equation discovered by Gauss, or Bain, however you want to say it. And it allows you to find the electric field at any point along a surface. It's especially useful for choking the crap out of ability to get some videos.
Jack, can we just continue?
Okay.
You can totally use that.
So you want to use this for situations where you have a wide area and where Coulomb's law would be too complex to use. So a Gaussian surface is purely imaginary, and you basically make the Gaussian surface so it's around the object, and so it's along a point where you want to find the electric field. And the kinds of Gaussian law shapes that you're going to use just depends on the problem. If you've just got a point or a sphere, you're going to want to use a sphere Gaussian law surface thing. But if you've got a cylinder, you're going to want to make your Gaussian surface cylindrical as well. And if you've got an infinite plane, you're going to want to use a square or a cube. And the reason that you're going to want to do that is so the Gaussian surface is perpendicular to the charge. So since Gauss's law is a dot product, that's cosine, that pretty much goes away because the cosine of 90 is 0. And then let's see, the cylinder, and then yeah, that's about it with Gauss's law. We're gonna do a practice problem with it anyway, so you'll see how it's done. Rest assured.